Welcome everyone. My name is Greg Ristabin from Olympus SSA. I'd like to welcome everyone to this webinar titled Fast Immersion-Free CFRP Inspection using the new Olympus Phased Array Wheel Probe. This webinar will provide an overview of the RollerFORM Wheel Probe inspection, including mechanical and phased array setup, acquisition, and analysis of composite defects using the Olympus OmniScan SX and OmniPC for offline analysis. Our presenter today is Chris Magruder. Chris is the Phased Array AUT Manager for Olympus and has been developing and delivering phased array systems for over 12 years. He works with service companies and end users of all levels all over the world, providing phased array application development and support. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. The chat panel will not be monitored during the course of the webinar. If we aren't able to get to your questions, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, take it away.
Good afternoon, everybody. Good evening for some of you. I see we have another very big turnout for the webinar. I'd like to thank everybody for joining us. Today, we're going to be learning about the latest exciting new product from Olympus that's a perfect companion for the OmniScan SX and MX2 in their RollerFORM Wheel Probe. The RollerFORM Wheel Probe is designed to provide an immersion-type inspection on CFRP, that's carbon fiber reinforced panels, aluminum panels, and similar components typically associated with the aerospace industries. Through the presentation, you are going to receive, after the presentation, you're going to receive the individual training presentations and videos that accompany the RollerFORM. That will include all of the slides and some more detail. So no need to screen capture unless you just want to. You'll receive all of that information in the follow-up email. The RollerFORM is a ergonomically designed, lightweight roller wheel probe that contains a phased array probe inside a water-filled tire chamber. It includes several mechanical adjustments that we'll be learning about. Key features include this specialized tire material impedance matched for water, a specialized phased array probe that comes in several sizes and frequencies and designs we'll learn more about during the webinar. There's several mechanical adjustments. The wheel probe includes a laser guide system for accurate scanning and some integrated buttons that work with the OmniScan to make acquisitions fast and simple. It's a perfect companion to the OmniScan SX or MX2, and this presentation will take us through the setup of the OmniScan, the mechanical fine-tuning of the inspection, including the C-scans and acquisition. So prior to setting up the OmniScan for the wheel probe, the tire must be filled with water using the in and out valves in accordance with our manual. The recommended water is distilled deionized water for best results to keep the chamber clean and free of mold and mildew as best as possible and bubble free. Best practice is to fill it the night before to allow the water to completely degas. The bubbles are apparent through the tire material, and there's a bubble trap on the right side, the left side wheel flange, that a slight shaking of the tire with the wheel flange in the highest position for the exit of the air traps the bubbles. It's very useful. It need not be pressurized with water, just filled completely. And a good fill is apparent when we have approximately a 2 millimeter gap between the plastic wheel flange and the component. And if we rock the wheel probe just a little bit, we can see that edge tapping. We don't want too much water in it or it distorts the tire material and requires a little extra pressure that's not necessary. There are several mechanical adjustments on the RollerFORM. For convex-shaped components, there is a wheel and skid plate in between the primary rear wheel that will allow as a guide. This is locked and unlocked using the red handle. It's lowered into position snug against the component and relocked. For flat surfaces, flat panels, flat CFRP, it need not be used and can stay raised up off of the component. So we're going to start with preparing the OmniScan phased array instrument for use with the 0-degree linear scan that the RollerFORM wheel probe is designed to generate. We're going to start going through the wizards for the part and setup. We're going to configure the UT. We're going to work to configure the synchronization gate. The synchronization gate is a feature normally associated with immersion tanks that allows stabilization of the surface interface signal for a really clean, precise C-scan. We're going to build a manual TCG for our sensitivity, and we're going to configure the detection gates and C-scan configuration. Normal day-to-day use of the RollerFORM is accomplished by opening a pre-configured data file or setup file with the probe frequency selected. This presentation is designed to take us through the entire setup from scratch as well. But again, normally we save the file and make a few minor adjustments for component-to-component inspection. So for any application in the OmniScan, to clear out all existing configuration and start with a default blank A-scan, we're going to select File from the main menu and New. This will clear out the group and give us one default A-scan. Then we move into the wizards. On the part wizard, we're going to enter the thickness of the component and select Material Composite. The thickness entered here will have some default value in the color palette and the gate logic, maximum and minimum positions, and selection of the material of composite will associate a longitudinal velocity of 3,000 meters per second with the inspection. Continue in the wizard and select Next, where there's no weld associated with this, and Finish. That will conclude the part wizard, moving to the setup wizard. In the setup wizard, on your first step, you're going to see a group mode, and depending on the instrument model, either an OmniScan MX2 or SX, and the pulsar configuration, there could be several options here. The RollerFORM wheel probe is a phased array inspection only. Select phased array. And for the technique, we're going to select 0 degree. The three available techniques that we see here set defaults for the displays, the gate modes, and the color palettes, and they will shortcut our setup a little bit and put the OmniScan in a condition most favorable for this application. Continuing on in the wizard, we will see the auto detect on. All Olympus phased array probes contain a chip that contains the essential variables for the calculator, to include the model, the frequency, the number of elements, and in this case we're going to be using a 3.5 megahertz 64 element probe that has a center-to-center element size, also called pitch, of 0.8 millimeters. The reference point in the probe is the measurement from the edge of the casing to element number 1 inside the wheel. The phased array probes are designed and optimized for a near wall inspection, with element 1 on the far right side of the RollerFORM adjacent to this plastic wheel flange to be as close to the component or to the edge of the component as possible. The left side of the probe is not utilized here and contains a little bit larger wheel flange that also contains the bubble trap. The natural scanning pattern is going to start on the bottom right, moving forward, and indexing left to right that we'll learn a little bit more about. The several different probe models are available now in different frequencies. All of them are designed to be used in water with an optimized impedance matching layer in water for the probe surface. On any probes in the Olympus catalog where you see a CCEV, it means that the probe contains a mechanical focus in the lateral direction for optimized and improved length sizing on the scan axis. In other words, we're combining a mechanical focused probe along with the phased array focusing for a more precision inspection. The upside of using a CCEV probe is that length sizing is improved. The downside is once that radius is made, it's relative to a finite range of thickness, which for the composite inspections, normally most of these that we see are a couple millimeters to less than maybe 20 millimeters thick. Moving on to the probe selection, continuing through the setup wizard, the wedge selection, continuing through the setup. The wedge or the RollerFORM wheel probe is not automatically detected. It is selected from the database. The wheel in the tire material contains a 25 millimeter standoff in water to put our surface reflection far enough out in time it doesn't interfere with our inspection. It has a wedge material that is water of a water velocity, and it is optimized for a normal 0-degree inspection. The offset for the wedge, and anytime you're using a Olympus wedge from the wizard, as soon as I select this wedge, the reference from the probe is no longer needed, and the reference becomes from the edge of the wedge, and in this case is the far left side of the wheel flange that contains the bubble trap. So we have a 64 millimeters from this side contains element number 1. Continuing on in the setup wizard, we select a skew of 90 degrees. The skew represents the beam orientation in relationship to the mechanical movement, which is also the scan axis or a blue ruler, and should be left at 90 degrees. And our index offset for now is going to be left at 0. And we'll talk a little bit more about the index offset when we get into inspection preparation. At this point, the probe, the wedge, and the component have all been entered, and those parameters are known to the software. Now it's time for the fourth part of our group, which is the focal law. And again, all calculators for phased array, regardless from Olympus or OmniScan or TomoView, contain 4 parts: probe, wedge, material. Those are all hardware with physical parameters that can be measured. And the fourth part is the group formation or the beam formation that we're asking from the software. Select leg 1, which represents the beam plotting for the inspection. These inspections are going to be a single leg inspection between the probe or the water to tire material interface on the component to the back wall. The material was selected during the setup, and the wave type is not selectable here because this type of probe and wedge or water it only generates a longitudinal wave type. So skip through this and select next. And this brings us to the beam formation or the configuration of the focal laws. It contains 4 parameters. The first determines the element quantity. The element quantity will define the size of the beam by adding or subtracting elements from the quantity. With a 0.8 millimeter pitch probe using 4 elements, we essentially have the equivalent of a conventional 3.2 millimeter probe. The number of elements here will also affect our total coverage between the first and last element, as this is beam to beam center point. So for most composites that we see, the default value of 4 is sufficient. For a thicker or more attenuative material, you may need to add 6 or 8 elements to penetrate and get a good backwall signal. That can only be determined by experimentation and is a function of the probe frequency and the thickness and attenuativeness of the material. We want to use the first and last elements of the entire probe from element 1 to element last, in this case 64, and we're going to step every 1 millimeter. So this would mean focal law 1 is elements 1 through 4. Focal law 2, or A-scan 2, would be 2 through 5, 3 through 6, and so forth. So on the electronic or probe side, on the index axis, we have a 0.8 millimeter resolution, the pitch of the probe. And there's also the possibility of what's called improved resolution or half-step resolution. For a more precision inspection, where we want to step smaller than the pitch of the probe, entering 0.5 at this step will create a focal law or A-scan of 1 less element in between every A-scan, similarly to the previous slide. That has the effect of creating a simulated or electronic version of a half an element. In that case, we would be stepping every 0.4 elements. The upside is a much better precision inspection, but the downside is the file size will be twice as large and the scanner speed half as much. And if that's not a consideration in the inspection, it's possible. This is the same function as improved resolution in the TomoView Advanced Focal Law Calculator. Select Next. At the end of the focal law wizard, the software gives us the opportunity to set our gate as to shortcut some of our setup. It has nothing to do with the actual focal law creation. A good starting point would be about 1 to 2 millimeters. We want the gate as close to the interface signal as possible, and we need enough width to include the gate A, the red gate A, all the way over the back wall. We'll fine-tune this once we get into inspection preparation. Select Next. And at this point, we have completed all of the wizard steps for the probe, the wedge, the material, and the beam formation. And we are looking at the A and S scan. If the A and S scan wasn't already displayed, from the interactive title bar at the top of the screen, selecting Layout allows you access to all of the different layouts, and select A and S. At this point, we can see this is the water inside the tire material. This is the interface signal of the tire material to the component, and we have a very light detection of the component here. We can also see that as the probe is moved in the RollerFORM back and forth and side to side, it has not been stabilized yet. We see a few millimeter difference on one side of the probe inside the tire material than the other. And this can be due to pressure or the shape of the component or just a normal use. The probe is stabilized inside the material, but we will use a synchronization on echo to flatten this shortly. This is a normal looking indication when you're initially leaving the wizard setups. So the OmniScan has 3 visible gates. A red gate A and green gate B are detection gates, with red being the primary detection gate. Regarding the gate that's used for the calibration functions. The third gate, which is very relevant to the RollerFORM wheel probe application and to immersion tanks, is called an A-scan synchronization gate. It allows a synchronization on echo so that it aligns the crossing signal of the I gate to be set directly at 0 millimeters. The crossing signal that we set here, that function of the gate was also determined when we selected 0-degree linear scan in the PA mode, the mode during the wizard setup. It's normal that the yellow gate disappears when we're in A-scan synchronization mode because it's dynamically updating for every A-scan to build the S-scan display, similar to an immersion tank. And as we can see, once we enter A-scan synchronization mode, the yellow gate disappears and my interface signal is completely flat and straight and automatically aligned at 0 millimeters. This is a very important feature for either a RollerFORM or an immersion tank, as it allows precision measurements inside the C-scan to be relative to 0 instead of relative to the distortion of the probe in the tank or the wheel form. The normal mode for this would be pulse. And again, our signals, both for the A-scan, both for the gate A for the detection readings and for gate I for the synchronization readings, are going to be using the first peak that crosses the gate and the edge of that peak. And these functions for the A-scan gates are also included in the readings that are associated with them. After we've gone into synchronization mode and stabilized the signal through the water path, there's a second mechanical adjustment in addition to the middle wheels and skid plate that was associated with this knob. The second mechanical adjustment allows us to rotate the probe clockwise or counterclockwise to optimize the probe orientation directly at 0 degrees to the component. When I move this adjustment, I can see the amplitude of the interface signal either rising or lowering. So I'm going to peak that up to where it's optimized. And when it is, I will lock the probe in place. And on a flat plate, this is locked in place between the stabilization of the rear wheels and the roller plate. Or in a convex inspection, it would be stabilized between the middle wheel and skid plate and the probe. So it loosen the probe with this knob here, turn it just slightly counterclockwise or clockwise to optimize the interface signal in amplitude, and lock it back in place. After we've done that, we want to go ahead and fine-tune our range so that we have a normal looking display. Start the range at -1 or 2 millimeters so we can see the water column just on the other side of the tire material inside the wheel. Any bubbles that were interfering with the inspection can be seen here. This allows us to validate that the whole S-scan is being detected in the interface gate from the yellow gate I, and set enough UT range so that the back wall is completely covered, so that the back wall is completely visible plus a few extra millimeters. At any time, in full screen mode or with the menus visible, tapping on the first half of the UT ruler, which is purple, will enable the operator to adjust the UT start. Tapping on the second half of the ruler will enable the operator to manipulate the UT range. Similarly, tapping on the dB area or the gain area behind this display in the upper left-hand corner of the OmniScan display header allows the operator to manipulate the gain, hardware gain, using the rotary knob on the side of the instrument. So we're now in synchronization on echo or A-scan synchronization mode. We have built the group, which is the sum of all of the focal laws in the S-scan and make up the group 1. This is a single group application. And now we're moving on to the UT configuration. Most of the UT parameters are very similar to a single channel conventional flaw detector in that what we do to one applies to all of them. So we're going to start under the UT menu, under the pulsar submenu, and select the voltage or energy for appropriate for the inspection. Voltage selection is a function of the element size in the probe, the element frequency, the attenuation of the material, and the thickness of the material. Too low of voltage results in unnecessary gain, resulting in poor signal-to-noise ratio. Too high a voltage will give us a saturated signal even at 0 dB. So I would suggest starting at 80, we found for most of the composite inspections seems to work very well, but adjust this appropriately. The pulse width need not be adjusted. It was automatically selected when the probe frequency was detected by the software. Select optimum for the PRF option. The optimum is a balance between scanner speed, battery life, and performance. And in the optimum condition with the standard setup, we can see we still have 178 millimeters per second, which translates to about 7 inches per second scanner speed. Continuing the UT configuration to the receiver. The composite CRFP inspection is typically used in half-wave negative rectification, but use what works best through experimentation. There may be aluminum panels or other applications that would be better suited for that. Typically, video filter is off, so we don't get a smoothing effect between the multiple amplitude peaks of the interface, or it doesn't attempt to smooth the individual layers in the composite inspection. Averaging and reject maintain the defaults. And filter selection. For the short version is to use the filter that works best. When no filter is selected, we are benefiting from the full bandwidth of the probe frequency, and as soon as we select a filter, it's going to crop off portions of that. Use what works best, but don't be surprised if best results are achieved with no filter selected at all. Under UT Advanced, change the point quantity to auto. The auto point quantity will ensure a low scale factor and compression factor regardless of what range is being used. The CRFP inspections and typical aluminum panel inspections in the aerospace industry are typically short range, and this isn't an issue like in weld inspection where it becomes critical function of both file size and acquisition speed. So auto is sufficient. So at this point, all of the UT configuration is complete. Our interface signal is good, and we're preparing now to move on to the next step. In general, the 0-degree linear inspection, both for aerospace components or for any corrosion type inspection, is defined by its near surface resolution. It's something we want to be mindful of in our setup all of the time. And what the near surface resolution means is the smaller we can make this signal, the better our inspection is, or the more likely we will find a flaw and be able to gate it on our first attempt near the surface. This gate position will need to be as close to this as possible, and again, we'll fine-tune this and talk to it a little bit more when we get into inspection preparation. So we also, for our good inspection, here is our surface interface signal, and here is our back wall. We need to make the back wall as large as possible without increasing the size of our surface interface, which would hurt our near surface resolution. So the way we go about doing that, how do we raise the amplitude of this signal without raising the amplitude of this one with the hardware gain? We're going to use a manual TCG. Select Menu Sizing, Submenu TCG, and select TCG. After TCG is selected, select Curve Setup, and you will see a default 0.1 with no gain at 0 millimeters by default. We're going to move the position, and we can see the TCG point is the white dot right at 0 amplitude on the UT ruler. We're going to increase the position here to move our TCG point slightly off the interface so that no gain is realized prior to the TCG point. Select Add to create TCG point 2. And by the way, this same TCG curve is applied to every A scan. This is A scan first. This is A scan last on the S scan. It's applied evenly to all of them. So on TCG point 2, change the position until the white dot, which determines the current TCG point, is directly on the backwall signal like we see here at 5.82 millimeters. And manually increase the gain here until the signal is approximately 75 to 100% amplitude. Since we're using a first crossing signal, it doesn't matter if this signal is saturated or not, but the best of scanning techniques would normally have it pretty close to 100%. This ensures a minimum loss of data in the gate and a maximum acquisition for our C-scan creation. So it's time to add the C-scan to the inspection now that we've fine-tuned our UT and our inspection sensitivity. From the interactive title bar, select the layout by tapping on this area in the touchscreen and select the ACS layout that will enable the C-scan. The default C-scan that you see now is a time-based C-scan that will move at the speed of the pulsar based on the inspection resolution, and we can see it's based on time from our clock acquisition that we see here. Change the gate thickness source under the gate menu, submenu thickness, select source, and we're going to use for the color palette and for our readings the signal in gate A crossing here minus the signal in gate I crossing here. That will ensure a stabilized reading from 0 millimeters at the surface interface. Enter the minimum and max. This is defaulted to the part thickness and it can be adjusted. This thickness range here will determine the purple scale that we see here, and it can be shortened during analysis mode as part of fine-tuning our analysis. Continuing on to the display color palette, select Menu Display, Submenu Properties, Color Palette Depth, and by default we'll see the same scale here. In the previous slide, that min-max range controlled the purple ruler on the UT reading here, and this will scale the color palette over that value from red to blue. And that can either be a compression or exclusion mode. And we can see here that the color pixel seen in the C-scan is a function of the arrival or time of flight of the leading edge signal in gate A, and its color is determined both by the scale that we see here under the UT gate thickness, source, and the color palette distributed. As I change the color palette min-max, I will also see this contrast change inside the C-scan. The default values are normally a great place to start. So at this point, our configuration of the OmniScan, not including the hardware from the RollerFORM yet, is complete. The phased array was configured for a linear 0 sector scan using all 64 elements of the probe. Our gate mode position was optimized. We are in A-scan synchronization mode that was determined from our yellow gate I, and we saved the file by a press and hold on the file name area of the OmniScan header. Select Save As, and a dialog box will pop up to allow us to save the file on the SD memory card. The next part of the presentation, and this is a separate presentation in the follow-up files that you'll receive from this webinar, is a configuration of the hardware on the RollerFORM wheel probe with the OmniScan. So that's going to include the configuration of wheel encoder 1, which is associated to the scan axis. It's going to configure the increment button that we see here on the RollerFORM that works as a clicker on encoder 2. And it will include the configuration of the DIN, or digital input button, for start acquisition and clear inspection, for repetitive inspections without having to touch the instrument. So the first part of this is the encoder 1, and to put the instrument in encoder 1 scan. So we're going to select Scan Menu, Inspection, and we will change our type from time that we saw a little clock in the notification area to raster. When we select raster scan, it will slave one of the encoders that we select to the scan menu. So when we select encoder 1 here, which is wired to the wheel on the rear wheel guide, it will slave this wheel encoder to the blue axis, also called the scan axis. Selecting Scan Encoder allows us to configure the resolution and type for the wheel. This is a standard Olympus quadrature encoder. It has a resolution of 12 millimeters that is written on the encoder. You can also calibrate the encoder if that's part of your procedure, or if something has changed that would have affected the resolution under the wizards for calibration and encoder. We can inverse the polarity and change the direction for scanning forward or backward. This encoder 1 is slaved to the scan axis, which is also always visible in the interactive title bar. When this number is red, it means that the current encoder position is outside the defined area of the C-scan. When it's blue, it means it's inside. The wheel encoder has a second position that it can be installed with instructions in the manual. So for smaller components, small radius components or convex components that are not utilizing the rear wheel guide, the encoder is working directly on the wheel flange of the tire. And there's detailed instructions for moving that in the instruction manual, and the encoder cable here is integrated into a nice ergo handle that includes the umbilical back to the instrument with the encoder and digital input cables. Okay. Select Scan Encoder and change from encoder 1 to encoder 2. Encoder 2 is going to be a clicker and preset type encoder, and it has a resolution here that's automatically determined by the software based on the phased array configuration. We're going to talk about this a little bit more in a few slides, but the software knows at this point that center beam 1 to center beam 2, or center beam last, is 48.8 millimeters. So every click of this button will index the index axis position 1 stroke, or 48 millimeters, as it's incremented. And the normal inspection process for that is we have slaved the scan axis wheel encoder 1 to the blue ruler. So as I move it forward, we'll see that incrementing here. As I click the indexer button, it's going to increment me over. So I'll take one line scan to the end, reposition the RollerFORM, click the button, and it will automatically be ready to take the next acquisition. There's a second button available on the RollerFORM handle on the right side, which is associated with the digital inputs that come through the same cable and connector as the encoders. These are configurable and programmable inside the software. So select Menu Preferences, Set Up, and turn the state off. When the state is off, the options appear for the DIN, and there's several of them. DIN 1 is the only one that's wired to the RollerFORM. So any of these options are available, but the one that's defaulted in the setup files that are provided and the most useful for this day-to-day operation is the Clear All. So when I click this button, based on my configuration here, it's going to clear the C-scan data, and it's going to set both encoders back to 0, indicating I'm ready for a new inspection. And we do that just after repositioning the scanner correctly. So at this point, the phased array and UT has been set up. The hardware for the encoders and the digital input that interface the RollerFORM to the OmniScan have been set up, and we're ready to start preparing for an acquisition. Our normal process for an acquisition would be to recall a pre-configured setup that we've just completed, enter the component thickness, for this is a new inspection and it'll probably change every one. We're going to fine-tune our sensitivity, fine-tune our gate position, define the current C-scan area and inspection resolution, and then we will inquire data and save file. So again, you're going to be provided default setup files with all of these parameters configured. This third presentation is designed to be used with either one of those files we've provided or the file you would have just created that we went through up to this point. On the OmniScan name, file name area, press and hold, and it will, or go to File, Open, and we'll see under the Setup filter the various setup files for the RollerFORM or the ones that we've already created ourselves. So we initially input the part thickness during the group wizard. This same parameter is available from the group part menu, part submenu, and enter thickness in millimeters or inches, depending on which mode the instrument is in. We're going to fine-tune our gain a little bit, which will mean adjusting the TCG point either directly over the back wall of the new component's thickness and raise and lower the gain. So we're going to make a hardware gain adjustment or general gain adjustment that will raise and lower both of these. And I'll make a TCG gain adjustment in the same spot that we saw earlier just to try and maximize this signal here. Okay, we're going to optimize our gate. The gate is available from the touch screen. If I touch the gate in this area here, I will get the start in the upper left-hand corner. The middle, I will receive the threshold, and tapping the gate on this end, I can adjust the width. These are displayed here under the gate submenu. So we want to put this gate as close as we can to the interface so we don't interfere with the inspection. The result of putting the gate too close to the interface means that it will generate red pixels of the shallowest readings throughout our C-scan. This can be changed in analysis mode after the inspection at any time because all A scans are saved. The width of the gate needs to include the total back wall, here. The threshold needs to be high enough so it doesn't include the layers of this isn't baseline noise, but the actual composite layers. There was a question about what options, if any, are available on the probe width. There are two options for both a 32 element, a small version of the wheel probe, and the 64 element. The 64 element probe would be 64 total elements times 0.8 So if you were theoretically using a 1-element aperture, the maximum width would be 51 millimeters. With 4 elements, it would be about 48. And in the follow-up presentation to this, and in the brochure that will be included with it, there are several options, and those probe details are and specifications are laid out. Another question, is there an encoder-less version for a purely manual inspection? And there is not. I assume that would just be for a cheaper version or less expensive version of the RollerFORM. But the RollerFORM and the OmniScan is capable of using it in time mode for a timed-based C-scan. You could just scan completely in one direction nonstop, but there wouldn't be any relationship to the scan axes. We're going to fine-tune our C-scan a little bit for the index offset of the probe. When we selected raster scan from the scan inspection type, the software automatically moves the 0, 0 position on the probe to the center of the probe. This is a feature that's used in immersion tanks that makes rapid scanning with overlap extremely convenient and fast. Most customers prefer to move 0, 0 onto wheel probe type inspections to the far right beam center point of focal law or A-scan number 1. Whatever number you see here as a result of the aperture you programmed, entering in a number opposite that of, in this case, 24 instead of -24 will offset this value back to 0, 0. This indicates that 0, 0 is directly under the first A-scan of beam center point number 1. Select Scan, Area, and this is where we define the C-scan. Since we selected a raster scan under the inspection type, we have available parameters for the scan axes, which would be axis 1, which is slave to encoder 1, and we have an index axis that is applicable to the green ruler, which is a function of the width of the probe. So initially, when I click this, the software is automatically determining the beam-to-beam center point from my current configuration. So if I had a 0 here and a 0 here, the software would give me one stroke. It would be 0 to 48 millimeters for a single line acquisition, either on a time or the encoder. Every successive increment of this value is another stroke. So 96 millimeters here is telling the software I'm going to have stroke 1 at 0 millimeters. I'm going to hit my indexer button and take stroke 2, which would be 48 millimeters. And the last stroke, 3, would start at 96 and end at 145. So under this condition, I'm going to be taking the inspection information for every focal law or the S-scan in 1 millimeter on the scan axis, and that's a mechanical resolution. And on the electrical resolution of 48.5 millimeters, I'm going to take 3 strokes. So I'll enter 99. And again, you don't have to do the math. Just turn the knob on the OmniScan with this value set, and it will automatically increment. I can also reduce this to any number I want as well, and then it's dependent on the operator to align the scanner in the correct position prior to taking the data. And as we can see here, under this, it represents beam center point 1 to beam center point last. When a red C is present in the upper left-hand notification area of the OmniScan header, it's an indication that the C-scan is in compression mode. Compression mode occurs when there are more data points in the C-scan than available pixels on the window of the OmniScan or on the window of your computer, which would be based on the size of your monitor. Compression is very important for this type of inspection because it ensures you don't miss a critical data point. when in compression mode, the software will allow 1 pixel in the C-scan to represent 4 or 16 pixels in the data, and it will ensure that it's always displaying the pixel color of most relevance, which is a thinnest color for 0 degree and position C-scans, or the maximum amplitude for amplitude-based C-scans typical of weld inspection. Zooming on the C-scan will eventually make the C go away. It's completely normal to do analysis while we are in compression mode, as we can be sure not to miss a critical pixel from the compression feature. So the natural scanning pattern is going to be from the lower right-hand corner scanning right to left. This is optimized for a near wall inspection, so element 1 is as close to the plastic wheel flange inside the tire material as possible. Element number 64, or element last, is approximately here in the wheel probe. And again, we have a bubble trap on this side of the wheel flange. Placing the RollerFORM with this wheel flange at its highest position, gently tapping on the roller material on the tire and moving it around and tapping on it, we can see the bubbles inside through the tire form. It's opaque, and they will be trapped in this, so it's very efficient. Even when there are bubbles present, they only degrade the inspection on an overhead inspection where the probe the bubbles are in between the probe and the component surface. In normal flat or even angled inspection, it's not normally a concern, but it's very easy to get rid of them using the bubble trap and the out valve as well. So we're prepared for the inspection. We've got our acquisition ready, all the phase array, the encoders, all the hardware. We've configured our C-scan. I moved the beam center point directly under focal law or A-scan number 1, which would be here and here. And I'm ready to start to do the acquisition. I'm going to turn on the laser and I'll twist it so that it's aligned straight with the component. I could have prepared ahead of time some chalk marks on the composite or aluminum panel to align my 48 millimeter stroke. I can have a scan speed of 178 millimeters per second. Again, that's very fast and typically a lot faster than most people would scan comfortably without losing data points. This wheel material is permeable, and saturating that real good with water prior to the inspection allows a very light spray. This picture is showing a lot of water, but it really just takes one shot from the water sprayer. A real light spray is sufficient. So we will select the Start Acquisition button here, and that will clear the C-scan here. It will reset the scan and index coders at 00, preparing us to take the acquisition. And I can also, we would normally be into full screen mode from the layout on the interactive menu. In full screen mode, I don't see the menu options here or here, and we see a much larger area of real estate on the display for our actual data. So I'm going to move the RollerFORM forward to the end of stroke 1, collecting the data. Again, this color palette was a function of our thickness and my configuration under the gate thickness source menu and the display properties color palette menu that control this vertical bar purple ruler and this vertical color palette scale. I move all the way to the end of the first stroke, and I continue scanning so that my scan axis is outside the defined C-scan. Why I do that is because when I reposition the scanner for my second stroke here, if I'm outside the area of my C-scan, I won't contaminate any of the last data that I have right here. So I finish stroke 1, reposition to the second stroke. If I have any missed lines of data from the encoder, moving too fast or too jerky, I can back the scanner up and do that. My scan speed is here, but any jittery or quick stop and start can generate these missed data point lines. It's a two-way encoder, so I can move the encoder, the scanner back and reacquire the data. It will always retain the last data taken unless changing the default in the OmniScan. So once the scanner is in position for the second stroke, it's normal I would have a long scan axis here. I hit the clicker button, and the clicker button is going to set the index axis to 48. It will reset the scan axis to 0, and I can complete the second line scan. I'll repeat the same process for the third line scan. And when the inspection is complete and the C-scan is filled, I will hit the pause instrument on the outside of the OmniScan here. I go to File, Data Settings, File Name. Double tapping any parameter will generate either the number pad or the keypad where applicable. Enter in a file name and select File Save. This will create the data file I just acquired on the SD memory card for analysis offline using TomoView or on the OmniScan. In the follow-up email to this, we'll see more information, including the presentation that includes the TomoView analysis of composite inspections. So that took us through the setup and acquisition, the configuration of all of the hardware and encoders, the setup and configuration of the phase array and UT properties from scratch. But again, our day-to-day business is normally recalling a file, modifying the part, the gate position, and C-scan, fine-tuning the gain, and continuing. So we're going to leave it there. In the follow-up email, you'll receive the brochure. There were a few questions that I didn't get to that I'll answer in the email blast as well. I want to thank everybody for joining us again and look forward to seeing you in the next webinar. Greg?
Thank you, Chris. On behalf of Olympus, I'd like to thank all the attendees for joining us and Chris for his expertise and participation in today's event. We hope the material presented was informative and useful. This webinar, along with the Q&A, will be archived on our website at www.olympus-ims.com. Everyone who registered for this event will receive a follow-up email, regardless of whether you attended or not, and you'll get the links to the archived presentation and the presentation data files. That's going to do it for today. Thanks again for attending, and we'll see you again next time.